Okay. All right. So, oops. Okay. Another thing I would like to quickly touch on is quiz two. I hope all you guys, felt okay about the quiz two. You know, like, like I specifically mentioned in the class, right? For what we tested in these open book quizzes, your best references during the quiz time would be the textbook, right? Lecture slides, lecture notes, and assignments, right? So you would be able to find probably a quick direction in those references on solving the problems. So some would, I actually have some slides would even give you direct answers, right? So like the last question in quiz two. Um, Now that executable bit, now I know I didn't talk about the executable bit in the class, but however, you guys should be able to see that in the lecture slides. I don't know how many of you actually checked the slides for the executable bit. The slide will tell you what will happen if you try to execute a non-executable page, right? So it would incur a page fault. So if a non-executable page gets executed, um, it is right there in one of the lecture slides. So um, now one thing about the grading on quiz two, I also need to make sure you guys understand some of the grading standards. So at the beginning of the quiz question sheet, we specifically mentioned that for quantitative answers, right, you must show your work to receive credit, okay? So answers that do not do so will not receive credit. That's what we put at the beginning of the question sheet. And as you know, all questions in quiz two, excluding question five, would have quantitative answers, right? So question 1 to 4, you would have quantitative answers for all those questions. So you need to show steps or work on how you got your answers, right? So so we ask for explanations, steps, or details on your work. A, because we want to know if you use the right concept or reason for your answers. B, it is really necessary, right, for any open book exam. I trust you guys all did the work on your own. But anyway, so many of you only put final answers for some of these questions. So, but I don't want to have you worry too much about that. But I do need to apply a small deduction right there. So I need to do that in my grading to be in sync with the grading standard used for the other section. So. Also, it is needed because, in fairness, a lot of you did put a great amount of details in answering your questions. So there is always that balance of fairness, we need to maintain in a grading. So I just want to make sure you guys, when you see your grading, here and there, you may see a little deduction and then you won't. So here I'm explaining why we're doing that, right? So, all right. Any question on that?
Are they graded? Because I think I saw a grade, but it's not there anymore.
Yes, they were graded. I posted the grades temporarily over the weekend, but then Dr. Roche and I, we talk about something, but the grades you guys that you guys already saw over the weekend probably won't change much, but maybe some of the grades will be adjusted a little, but
Okay.
yeah. So, but I will most likely post the grades somewhere like after Wednesday. So maybe Thursday, you guys will see the grades and the my comments in your
Okay.
yeah, answer sheet. All right. So, all right. Let me share my screen now. Uh, okay. All right. So, you guys can all see my slide right now?
Yep.
Yeah. Okay. Cool. Alrighty. So, all right. Let me see here. So, okay. So, uh, all right. So let's continue where we left off from last class. Hopefully, we will have four, including today's class. We'll have 4 sessions left for this for this class. So, and hopefully we can also cover some IO. But I will have to cover some of the IOs because the last assignment will include some IO questions. So in last class, I stopped at the multi-level indexing scheme for implementing file system, right? So I started the indexing node scheme by talking about, if we were to only use one level of inode, right? Like what you see here on this slide, one level, right? If we were to only use one level of inode, then and one level inode could take a lot of space in describing a big file, right? For example, it needs 64 megabytes just for describing a file of 16 gig, right? So now then I went on to show a multi-level indexing scheme could work better, but I wasn't clear about exactly why. So actually with multi-level inode structure, you would also need at least 64 megabytes for describing a 16 gig file, okay? So so for the same file size, you would need the same amount of space for the inode structure, if not more, right? In the multi-level indexing to describe the file. So, but the thing is that the big advantage of using the multi-level setup is what? Is it provides the flexibility that you can start the file descriptor of a file with a small one-level inode, right? You can start the descriptor, the inode, with a one-level inode, right? Then that structure can grow if the file size grows, right? So if you only allow one level of inodes, then for every file, you would have to pre-allocate. Say in a system, you allow a file to grow as big as 16 gig, right? But if you only use one level of inodes, then for every file, you would have to pre-allocate 64 megabytes, like we talk about, for that one level inode structure, right? For each file to start with, right? Because you don't have that multi-level, indexing like flexibility. So, but with multi-level indexing setup, you do not have to pre-allocate, 64 megabytes for each file inode. You could start with a small inode. This is similar to, what you guys have learned in the multi-level paging, right? Multi-level paging there, you can start with a small one-level paging. Then you can extend that to multi-level paging. If your virtual space to physical space translation needs more level of paging, right? So here it's the same. So you can start with a one level inode. Then as the file size grows, you would do multi-level indexing to accommodate the bigger file size as the size grows, right? And so the multi-level indexing provides that flexibility, all right? So I just want to be clear about that. So, all right, so last class, I also show you guys two different diagrams for multi-level indexing. So, one on the top and one on the at the bottom. So these two extensions are not exactly the same, actually. So the key difference is the one to the bottom, actually this one, right? It is a lot of real world file systems are using, okay? So this one, the one at the bottom would provide more efficient, efficient direct access, with this scheme. So I won't talk a lot about why, but I just want to make sure you guys know that I have one slide showing this kind of multi-level indexing, right? So the one on the top, you will have the direct blocks, and the last entry in the inode would point to another similar structure as the root node, right? But the one on the bottom, at the bottom, the extension there, you can see it's essentially different, right? So it also has the direct blocks, but then you will have this single indirect, a double indirect kind of a setup there, which we talked in great details in the last lecture. So, all right. So I want to say the one at the bottom is the one usually that a lot of modern file systems are using. Okay. All right. So last time I talked about, okay, we want to do some in-class practice. Actually, I do want to do that because this is directly related to what you're going to do in your last assignment, actually. So it would be a good time for you guys to do this. So we're gonna do. I'm gonna create two breakout rooms. Okay. So let me see how many of you here. Okay, 1, 2, 3, 4, 5. Can anybody tell me how many of you here? I have. Okay, nonetheless, I'm gonna only create two breakout rooms. Okay, so with each room like seven people. Okay, so okay, I'm gonna do that. I'm gonna have to have two persons, one in each group, to take a screenshot of this screen. So can I say, so Amy, could you take a screenshot of this?
Yeah,
Yeah.
I can do that.
Okay. And I will assign you and a group of people into one room. And Jonathan, I'm not sure if you're there. Yeah. Could you take a screenshot of this slide, and then I will group you to another group. Okay. Sure. All right. So let's do that. Hmm? It's weird. Okay. I will. Okay, so you guys took the screenshot, right? So I'm gonna unshare here. So I'm having trouble. If I'm sharing, then it's kind of hard for me to see all the screens. So, okay, so I'm gonna break you guys into two groups. So so create rooms manually. Okay. Oops. Oh, you guys come like, hello. Do you want me to assign you guys to a group? Mike? 4名天豪. Okay. So guys, you guys have like a 7 or 8 minutes, okay? All right.
Okay.
Okay.
Can you guys see this? The slide?
Yeah, I can see it.
Okay.
Mm-hmm.
Hey guys, so you guys will have like about 7 minutes from now, okay? All right.
Okay.
All right, cool.
Three indirect bytes, which each have 100 pointers, 2 data blocks.
Right.
So since we have 3 indirect blocks times 100 pointers, we basically have 300 pointers to data blocks, 300 data blocks, 4 times 300, adding on to the 4 times 10. And then for the double indirect, since we have it's the same logic as just the regular indirect, except instead of 100 pointers, we have 100 squared pointers on each in double indirect. So it's gonna be 4 times 2 times 100 squared, and then you add them all together and you get 81,240.
Very cool. Very cool. All right. Do you want to continue to the second question?
So can I ask you a question on that real quickly?
Yes. Yeah.
So do you not have to take into account like the amount of space that the block of pointers takes up?
Oh, yeah, you mean the overhead. So
Yeah.
sorry.
Yeah.
Oh,
So since you have
okay.
like 3 indirect pointers, doesn't each block of indirect pointers take up 4 KB? And then same
Yeah,
for the
that's a
double.
very good question. That's actually a very good question there. But here we want to first look at, what would be the largest. I see. You mean that the indirect and the double indirect blocks
Yeah,
themselves,
don't those
right?
themselves take up space?
Okay, yeah, you're right. You're right. So that's a very good point, actually, because in the multi-level indexing, you would end up with some overhead with this kind of setup. But let's just say we for now we ignore them because they're minimal. But that's very good, Jonathan. So you
Okay.
you would subtract actually those bytes. Yeah. So um, but for the largest file, you essentially what Alexei just described. I think it's more or less still accurate because you have that 10 direct blocks, right? And then you have 3 indirect blocks. So they're 100 each, and you have 2 double indirect blocks, and then they can be 100 square for each one of them. So if you add them all together, that would be the size. But again, the overhead is it's a very good consideration. But in terms of the largest file, this structure can describe what Alexei just said, more or less. That's sort of that's the sort of correct answer. So, but hey, I mean that's pretty good. So, what about the second? Oh, okay, I will let you maybe a second group like Jonathan. Do you want to? Thank you, Alexei.
We didn't get to this part yet. We
Oh, you
we
didn't get
literally
to this
just
part.
no, we literally just
Okay.
finished the first part.
Okay. Alexei, do you have the answer to the second question?
A little bit. It's
Okay.
more of a guess more than anything, but I believe the answer is 32,307. That block.
Well, how did you get that? 32,000. You said.
32,307. It's a guess more than anything.
Oh,
I
okay.
just
Okay.
yeah.
Okay.
So we need bytes, and we said we are going to convert from kilobytes. Then
Right.
yeah. So then we divided by 10, and then further divided by 4 because each block is 4 bytes afterwards.
Yeah,
It's a guess.
Okay, that's the right direction actually. Anybody else wants to add to what Alexei just said? All right. Okay. I guess time-wise we need to move on. But thank you guys for doing this. Actually, one of the questions in your final assignment would be directly related to this. Okay. So let's see how this works. Yeah. So for what Alexei said about question 1, let's just quickly put. So basically, yeah, what Alexei described was exactly correct. So basically, you have you have 10 direct blocks, right? So you have what do you have? See, so each block is what? Each block is 4 KB, right? Okay, let me adjust my pen here. Okay, so 4 KB, right? So what do you have? So you have 10 direct blocks, right? So you have 10 times 4 KB, right? Plus what? Plus you have 3 indirect, single indirect, right? That would be 3 times 100, right? Each single indirect has 100 blocks, right? So times 4K, right? And then you have what? You have 2 double indirect. So that would be 2 times 100 square, right? Times, times 4K, right? So you add all these together, it's actually, it's actually 81,240 kilobytes. All right, that's the answer, what Alexei just said. And let's see this, how did you, how do you answer the second one? So the second question is about show which inode blocks, right, we would need to read if we wanted to start reading at this particular position into the file. So this particular position is sort of like a kind of a logical position, right? So these many bytes into the file, right? So we are doing a direct access here, right? So first you want to see, you know, because it doesn't matter you have direct block or one level of indirect or two level of indirect. Each block is what? Each block is 4 KB, right? So if you use this position, this is for, so if you use the position, it would be 1,292,288, right? So if you use this divided by 4 KB, right? That will give you sort of the index of the block, like the actual index, like considering all these levels, but this will give you after you traverse all these levels, so this will give you the index to the you know, if you like sort of if you like all these indirect levels, if you expand all of them to one level, right? So what kind of index it will have? So you would, this would give you 315.5. Okay, so it's sort of like 316th block, right? So we know the first 10 blocks, they're direct blocks, right? So you use at 316 minus 10, that would be giving you 300. Let's just use 5, 315, right? Minus 10, it would be 305, right? And then you have 3 indirect blocks with 100 direct blocks each, right? So that will take, that will be how many blocks are there from the indirect pointer, like a 3 indirect pointer. That would be 305 minus 3 times 100, right? Right? Correct me if I'm wrong. If anybody wants to say anything, just unmute yourself. Okay, so that will leave 5, right? So after, so this is like sort of like you first you have 10 direct blocks, right? And then you will have like 3 single indirect pointers pointing to what, 300 blocks, right? So that means then after that you will have 5 blocks left. So these 5 blocks, they are into the double indirect block, right? So essentially, we need to read into the first double indirect block, actually, right? So, so that's essentially what block you would read for this position, right? So you would have to get past the 10 direct blocks, and you would have to get past the 3 single indirects, and then what you have is 5. 5 is like it would be in the first. Oops, I don't know, my pen is. So it would be in the first. What's going on here? So, all right. My pen is acting up again. So, but nonetheless, so this 5, it would be belonging to the first, it's double indirect, right? Any question about this? Anybody, everybody understanding what I'm talking about?
I'm sorry, so the answer was the first double indirect block?
Yes.
Okay.
Yes. Yeah, the first double indirect block, right? The pointer, like it points to, because you know, so you the 10 first is the 10 direct blocks, and then you have 3 in single indirect, right? And then what do you have left is 5 after the 3 in a single indirect, because those are counted as 300 blocks. So you will have the, so you essentially it will be the 5th block into the first double indirect block area. All right.
Got it.
Does
Thank
this
you.
make sense?
Yeah,
It does.
All right.
it checks out.
Okay, cool. All right, let's move on. So, so let's have a quick summary for the inode kind of file system implementation. So, again, inode is a sort of a file descriptor for each file. It starts from a root inode, right? It can be expanded to multi-level indexing. So the inode has all the file metadata, right? All the file metadata encapsulated in that inode structure. So each file has at least one inode, okay? So, you know, on your disk, typically 2 to 5% of the blocks there, they're reserved for saving the inode's information. All right. So again, every file needs at least one inode, and yeah. So these are all what I just talked about. Okay. All right, so let's move on to the directory implementation. Now, this is also related to the assignment. By the way, I will actually post the assignment like after the lecture today, actually. So I think like I need to give you guys a little more time. You guys can work on, so there will be 5 questions. 3 of them, they're file system related, and 2 of them, they're IO related. Okay, so at least you can work on the 3 file systems related questions. So what does a directory do? Okay, so as we also talk about briefly when we started the file system topic, a directory is also a file. Okay, so that is just like a regular file using, let's say using Unix as an example, like a directory, like a regular file, it also has its own inode, okay? So that inode also has the attributes and a block map for the directory, okay? But what's different or special about a directory then? Well, a directory contains records of files and subdirectories, right? So that's very much understandable. So these records of files are what we call the directory entry, right? So you have sort of a collection, a data structure there that would hold the records of all the files and the subdirectories under that directory, right? So this directory and like a kind of collection, sorry, this directory file and subdirectory collection provides the operating system the information to locate the disk blocks for the files under that directory, okay? So each file or subdirectory under the directory corresponds to a record in that directory entry I just talked about. So depending on the system, the record information may be, you know, the disk address of the entire file in the linked list scheme. It would be the number of the first block, or in the inode case we just talked about, the information would be the block number of the inode. I will show you guys a diagram so you guys will understand what I'm talking about. But in all cases, basically, the directory system maps the file name onto the information needed to locate the data of that file, okay? All right, so now your file name, we talked about that before. Your file name could be having just the ASCII characters, or the file name could have Unicode characters, right? So in addition to the mapping of file name to the disk blocks, we also need to worry about the file metadata or attributes for each file, right? In that directory entry. So so how do they get stored in the directory entry, right? So let's look at a few schemes how all these file information are stored and maintained in the directory entry. So there are basically three common choices, okay? We'll mostly just talk about the first two choices here. That would be fixed length records and variable length records, okay? So, so these two diagrams are basically what I just talked about. So you essentially, this is the directory entry data structure. It essentially maps each file name, right, to that file metadata, okay? And so the diagram A here is for sort of it's a direct mapping between the name and the attributes, and the second B diagram is a mapping between the name and the first disk block or inode. Okay, so so nothing fancy about this. So for the systems that use inodes, we can again. So each entry here, you can have the name, file name mapped to the inode of that file. Okay. All right. So here we're talking about each record here. Each record here has a fixed length. Okay. So that's the basic, that's pretty much a straightforward setup there. So with these record scheme, we have made the assumption that files have short or fixed length names, right? An example would be, I'm not sure if you guys used DOS before, MS-DOS. So MS-DOS files have a 1 to 8 character base name, right? That's just very short. You can have at most 8 characters for your name, for a file name, and an optional extension of 1 to 3 characters, right? In Unix version 7, that's a very old Unix version, file names were 1 to 14 characters, including any extensions. So, however, nearly all modern operating systems support longer variable length file names, right? So how can these be implemented? So, well, the simplest approach is to, we can set a limit, right, on the file name length, right? So typically, some systems, they use 255 characters for the file names, right? That would give you sort of like a big enough space for your file names, right? But for efficiency reasons, a different structure is desirable, right? So that would be variable length records, okay? That would lead us to the next slide. This is like for each directory entry record, it has a variable length, okay? That's what this means. So, the total record, each record it has variable length, but portion of that record contains a fixed portion. Okay, so let's say let's look at the diagram to the left here. So here, each directory entry contains a fixed portion to start with, right? You have the so this portion is kind of fixed, has fixed length. Okay, and then followed by the data with a fixed format. So the first two sub portions here, they're with fixed length. Okay, and again, usually the attributes there include the owner information, creation time, protection information, and some other attributes. So this is what we call fixed length header, right? And then this header is followed by the actual file name, which has a variable length. Okay, so in this case, you have this first file here. It's projected budget, right? That's the first file name, and the second file name is the personnel, right? So, and third is the full, right? So so you could have the variable file name, the variable length for the file names, right? But the first two sub portions of this record, they are fixed. They're with fixed length. Okay. So and each file name here in this scheme ends with a null character, right? Just as the convention used in the C programming. So, but a disadvantage of this method is this one is, when a file is removed, right? Then you would leave a gap, like with a variable length there, right? So like a variable sized gap is introduced to the directory, right? So, this problem is essentially the same as, we saw with the contiguous disk files, right? So you don't want this kind of, over the time, when you have files created, removed, then you could end up with fragmented directory entry, right? So, and that's not ideal. So another way to handle the variable length names would be the one to the right, okay? So this one is the idea here is to make the directory entries themselves all fixed length, and the metadata part of the file, they're all with like sort of fixed length, okay? But each metadata portion, right, would have a pointer to the file name in the heap area. Okay? So essentially, you just keep the file names together in a heap at the end of the directory, right? So, but the beginning of the directory entry, right, you have all these fixed length metadata for each file, right? So of course, the heap must be managed, and you could have this heap area could grow very large, and it could incur page fault, right? So while you process these file names, but a lot of modern operating systems, they use this this scheme to the right. So like you have fixed length metadata for all the files, but you have the variable length of file names. They are being kept at the end of the directory entry. Okay. All right. So so how to organize and store the file information is obviously the most important concern in the directory implementation. Searching the file information is another important consideration in the directory implementation, right? So let's talk a little about file search computational complexity here. So with all the designs we have talked about so far, directories are searched kind of linearly from the beginning to the end, while a file name has to be looked up, right? So in the case of if you have extremely long directories, meaning you have so many files or so many subdirectories under a directory, linear searching can be really slow. Okay, I'm not sure if you guys have had that kind of experience. I did have that experience before. So if you open a directory with so many files in that directory, it may, even a refresh, right, in that directory could be very slow, right? So, and searching a file in that directory could also be very slow, right? So some operating systems like Windows let you index the files. So your search of the files can be quicker, right? And when you do indexing, normally what kind of data structure comes to your mind when you talk about indexing? Anybody?
An array.
Array? Yeah, sure. Yeah, array is a good, but what about the search efficiency of an array? Well, array essentially is actually very direct access. Actually, it's very efficient. But setting up an array itself could take a lot of time. If you can put everything in an array, access time is almost zero, right? Because you know which index is having which. But another data structure would be a hash table, right? So essentially, hash table is also indexed kind of collection, right? Similar to array. But hash table can grow, right? And is more flexible. So a lot of indexing in the file system it is done by using hash table solution. So so that's one way to speed up the search, right? So you essentially you assign each directory table entry with a hash code, right, generated by using a hash function on the file name, right? So say the size of the table is n, each file is hashed onto a value between 0 and n minus 1. So and when constructing the hash table, you use the hash function to generate, right, a hash code of the file name for the file table entry, right? So if this hash code is not used, you could just create a mapping in the hash table for this hash code and the file entry. But if the hash code is already in use, right, you could construct a linked list to hold all the file entries that have the same hash value. But that's essentially, if you guys learn how hash table works, that's essentially what hash table needs to do. So the search or lookup procedure of a file entry in the hash table setup is also the same as what I just talked about. So what is the big O computational complexity for using a hash table search, right? So the best scenario would be what? Would be each file name having a unique hash code, right? Right. So in that scenario, you would have like what, O1 kind of a lookup time in that case, right? You guys know how hash table works, right? So if you have each file name have a unique hash code, then your lookup in the hash table is essentially just indexed into the, you directly, you use that unique key and you go to the hash table and you will find that, that element in the hash table right away. So that's essentially actually internally hash table most of the time, is actually implemented with internal array actually. So, and so if there is a linked list of file entries having the same hash code in the hash table, you would need to traverse that linked list, right, to see if the file name is present. In that scenario, the worst case is what? Is you end up with O to the N, no, ON kind of computational search time, okay? But people are arguing these days, you know, because most of the time, you know, this, you know, to set up this hash table, you know, it demands a lot of complex administration, right? So people are arguing, you know, most of the time, do you really need this? Is this hash setup is worth it, right? All right. All right, so that's pretty much the directory implementation. And I guess we need to move on to the next topic. I think for the log structured file system, we'll see if we have time to talk about this later. It's not a usual kind of file system scheme. We'll see if we have time to look into this. And the journaling file systems, yeah, we'll also skip these for now. We'll come back if we have time. All right, so let's talk about, well, let's first talk about free blocks management, okay? That's also one of the most important aspects of file system management, okay? So free blocks, tracking free blocks on the disk, right? So essentially, it's very much similar to the techniques you know that are used for tracking memory blocks in memory management, right? So essentially, tracking free blocks is tracking available and used blocks, right? So there are two major strategies, the same as what we talk about in the memory management for managing free blocks of memory. That would be, you know, a linked list or a bitmap, okay? This would be also related to assignment. So I'm kind of trying to get through these materials first. So, all right. So a free link, using a linked list for tracking the free blocks of disk space, you know, essentially, again, it's similar to using the linked list for tracking free memory space. Okay, so so here, you know, there's nothing fancy about the linked list, right? So, but what we do need to know here, you know, in the normally in the disk management, right? We also manage all these disk blocks, right? We manage the disk space in blocks, right? So usually, as I talk about it last class, so usually these days, a lot of systems, they use 4K for the disk block. Now in early versions of Unix, a lot of Unix versions, they used 1K for the disk blocks. But the Linux, a lot of the modern Linux systems, mostly they use 4K for the block size. Okay, so now you can see in the linked list case, you know, if so this is sort of a linked list, essentially a list of pointers, right, to the free blocks. So so essentially each pointer here in each entry of the linked list points to a what? Points to a consecutive block of free space, right, on the disk, right? It could be just one block of data there. It could be multiple blocks of data there, right, for each pointer. Like much like what you guys just had in the quiz 2, question 4, right? You know, again, that's memory management using the free memory management in the memories management. It's the same. So with a 4K block, right? Like a 4K block. So each 4K block can have what? Can have 1K kind of pointers, right? Each pointer has 4 bytes. Okay, and each pointer points to the next free block. Okay. All right, this is straightforward enough. So here, if we use the linked list for storing information for free blocks, right? So we don't really have we don't really incur any real storage overhead actually with this scheme. And if free blocks tend to come in long runs of consecutive blocks, the free list system can be very efficient actually, right? So think about again, quiz 2 question 4, if you, after compaction, right, you essentially only have one node in the linked list, right? So because why? Because you only have one big free chunk of memory there, right? So you only need one node in the linked list to track that, right? So essentially a pointer and the size of that chunk, right? So if you have a lot of a lot of gaps or holes with consecutive blocks, right? And this this linked list scheme can be very efficient. Okay. But on the other hand, if the disk becomes severely fragmented, right, keeping track of all these blocks could be very less inefficient, right? So you may want to just track individual blocks, right? Because your disk becomes fragmented anyway, right? All right, and also in some implementation, people want to sort the free linked list, the linked list free block management. They want to sort the list, so that you could have the biggest size of the gap at the beginning of the linked list. But essentially, with the sorted linked list, searching free blocks in that linked list would become much more efficient, right? If the list is unsorted, sometimes you would need to traverse the entire linked list to find a consecutive list of free blocks, right? So, again, in the quiz 2, question 4, if you use some strategies, certain allocation strategies like best fit, worst fit, next fit, you would need to search this linked list to find a big enough gap, right? So, the traversal of the linked list sometimes could be inefficient. So, all right. So we just talked about linked list, and the next one would be a bitmap. Okay. So bitmap it's used for tracking each individual block. Okay, it's not like a linked list. A linked list you just use it tracks the maybe a sequence of blocks, free blocks altogether, right? So, but in the bitmap scheme, it would be tracking the block availability for each individual block. Okay. So similar to what we learned from the memory management, a bitmap could also be a very effective way to track free blocks of storage. So it is straightforward. A bitmap is essentially each bit corresponds to one block on the disk, right? Some systems, they use 1 to indicate the block is free. 0 means the block has been allocated. But some systems, they use these values just opposite, okay? But doesn't matter. So the scheme here is that you use 1 bit to track each individual block on the disk, okay? So by the first look, so the bitmap may require less space, right? As compared to what a linked list needs, right? Since it uses only 1 bit per block, right? However, the bitmap would remember here again, the key difference here is that the bitmap would remember the allocation information for all blocks on the disk, right? So there could be more storage overhead actually using the bitmap for storing the free list information for all these individual blocks on the disk, right? Again, because in the, remember in the linked list case, if there are a lot of consecutive blocks, it may require a lot less space to track those blocks, right? So, so here, you can see in this picture here, you can see the size of the, you can see the size of the disk block unit is actually an important design issue here. So, the smaller the size of a block unit, the larger the bitmap will become, right? The larger the size of a block unit, then you would have a less number of blocks, right? So therefore, you would have smaller bitmaps. Okay, so how the bitmap is stored on the disk? Okay, so the layout is like this. Okay, so essentially, you need to you would group bits together in word units. Okay, so each entry here. So this is a sort of like a long array right here of entries, with each entry having what? Having 4 bytes. Okay, and we know 4 bytes in a 32-bit system, it's a word, right? A word is 4 bytes in a 32-bit system. So like what's displayed here. So, so each word here represents how many blocks? 32 blocks, right? So usually in a 32-bit system, you have 1 word with 32 bits, and that 1 word would represent 32 blocks. And for a 64 system, the word size would be what? Would be 8 bytes, right? That would be 64 bits. So each word in a 64 system would represent 64 blocks, okay? But as we just talked about, using the bitmap scheme, you would have to do you would have to label each block on the disk, right? And so as your disk becomes larger, the size of your of the bitmap also would be becoming very large. Okay. Let's see like how would that be the case? Okay, let's see how much space do we need to store this kind of bitmap for all blocks on a 10 terabyte drive. Okay, let's see. So we want 10 terabyte. Okay, we have a 10 terabyte drive. Let's see with this kind of scheme, like what kind of a size we need just for this bitmap to track the block availability for each individual block on this 10 terabyte drive. So let's assume each block has a size of 4K, right? Usually, let's say this is Unix, Linux system, 4 KB per block, okay? All right, so what kind of size we need for this bitmap? So this would be the case, okay? So it turned out just for this bitmap, it needs 80K. 80K blocks, okay? 80K blocks to save the bitmap information. 80K blocks actually is 80K blocks is actually 320 megabytes, okay? Because each block has 4K, okay? So 320 megabytes. Okay, how this is derived? Let's do a quick calculation here. Okay, so, all right, so 10 terabyte is how do you write 10 terabytes here? So it would be 10 terabytes. We know it's terabytes, right? That's 2 to the 40 actually. So that would be times 10. So one terabyte is what is you have essentially it's like 1K, right? If you multiply 1K 4 times, that would be 1 terabyte, right? Right. So you multiply 1K 3 times, that would be 1 gig, right? So 1,000 of 1 gig is 1 terabyte, right? So 1K is 10 to the power of 10, right? So this would be 1 terabyte, and 10 terabyte would be this, okay? So, and so this would be, so you use 10 terabyte, right? So how many blocks for this 10 terabyte? It would be 10 terabyte divided by 2 to the power of 12, right? Right? So we just talk about 10 terabyte is what? Is 10 times 2 to the 40, right? Divided by 2 to the 12, okay? And this would become what? This become 10 times 2 to the 28th, right? So you have, so for 10 terabyte drive, if you have each block occupying 4 kilobytes, then you need how many blocks are there? 10 times 2 to the 28 blocks. Okay? And we know each block, right? Each block, you need how many bytes to represent each entry here. Let me see here. So 10, oops. It's always having trouble at the end of, okay, hold on. Okay, I will just get rid of this here. Okay. All right, so let's see, 10 times 2 to the 28th divided by what? Divided by 2 to the power of 3. And this would be 10 times 2 to the power of 25th, right? And this would be 10 to the 10 times 2 to the 25th would be so you need these many bytes actually, right? Right? You guys follow? Okay, so you need these many blocks, right, for 10 terabyte drive, with each block having 4K size, right? So this is the total number of blocks. So for, each block you need 1 bit, right? And 1 byte has how many bits? 8 bits, right? So you need to, so this is 10 times 2 to the 28, that many bits you need to track all the blocks on the disk, right? So you use that total number of bits divided by number of bits in a byte, right? That would be 2 to the third, right? And this would be what? This would be 10 times 2 to the 25th bytes, right? You need these many bytes, right, for the bitmap, okay? And if you need this many bytes for the bitmap, for the total bitmap, you need to save this bitmap to the disk, right? Then for these many bytes, how many blocks, how many disk blocks you need to save this, these many bytes? You would use this, right? Use this total number of bytes divided by 2 to the 12th, right? Because this is a 4K, right? 4K bytes, right? So this would be, and then you will get about 80K blocks. Okay, so this means just to save this bitmap, right, for tracking all the blocks on the disk, you need to have this bitmap needs to have this kind of, needs to have 80,000 blocks on the disk to save this bitmap, okay? You guys will have some exercise of this in the assignment. So, and of course, when you use this bitmap, you don't have to load all the, all the data from this bitmap into memory. Usually, it's possible to just keep 1 block in the memory, go into the disk for another, only when it becomes completely full or empty for 1 set of bitmap. So you could load this bitmap incrementally. That's what I meant. All right, let's just finish this and we'll end the class today. So bitmap is if you track all the blocks on the disk for their availability to see whether they're allocated or not. Bitmap overall, it does, because you only use 1 bit for each block, the storage there is kind of efficient. It provides a simple way to keep track of free blocks in a fixed amount of storage, right? Because the size of the bitmap depends only on the size of the storage space and the size of the block size for what we just exercised. But the main problem with bitmap is actually why it has been decided to allocate, say, a K blocks contiguously, right? So if you want to allocate like a string of blocks contiguously, the file system must search the bitmap to find a sequence of K consecutive 0 bits or 1 bits in a map. And that search can be very expensive, okay? So searching a bitmap for a sequence or a consecutive sequence of blocks of a given length is a very slow operation, okay? So that's a big drawback of using the bitmap. Other than the storage problem we just talked about, the bitmap could be very large with a very large hard drive, but the search in the bitmap to find a sequence of contiguous blocks can also be very slow. All right. All right. I guess we're out of time. So let's end the class today. Any questions, guys? You guys are all comfortable for what I talked today? All right. So
Yeah.
let me, thank you. Let me stop the record.